The use of p-values in hypothesis testing is a very important and useful concept in statistical inference. But let's start with a non-statistical example. Suppose a father tells his daughter that she can't play rugby that afternoon. Now, this isn't a sexist story. Girls can certainly play rugby, but it's just that she's not going to be supervised that afternoon and he doesn't want her getting injured. However, he's not going to be able to directly observe whether or not she plays rugby. He's going to have to make an inference after the fact based on what he observes at the end of the afternoon. And so the father will start with an initial assumption that his daughter didn't play rugby, and then he's going to evaluate the plausibility of that assumption based on his assessments of what's the chance that I observe what I see, for example, that she's clean or that she's dirty. What's the chance that I observe what I see if that assumption that she didn't play rugby is true? And then if that seems quite unlikely, or if it's unlikely to observe what I did, if the assumption that she didn't play rugby is true, then he will reject that initial assumption. So the key here is how likely or not is it to observe what I actually observe if the assumption of not playing rugby is true. So let's think of some different scenarios here. For example, suppose at the end of the day, the daughter is clean, right? That would be quite likely if she didn't play rugby. And so maybe we think there's a 95% chance of observing her being quite clean at the end of the day if she didn't play rugby. Now, instead, suppose at the end of the day, you observed her being hot and sweaty. Well, there's different ways in which you can get hot and sweaty, but maybe in this case, you assess that you think there's only an 80% chance that this would be true if she hadn't played rugby. Now remember, this is not the probability that she played rugby or not. This is not the probability that your initial assumption is true or not. This is the probability that you would observe what you do, for example, being hot and sweaty, if the assumption is true. Now consider a third scenario. In addition to being hot and sweaty, maybe at the end of the afternoon, daughter is muddy. Now, in this case, we might think, well, there's only a 35% chance of observing her being sweaty and muddy if she actually didn't play rugby. Once again, this isn't saying that there's a 35% chance that she played rugby or not. This is saying that there's a 35% chance that we would observe her being muddy and sweaty if the assumption that she didn't play rugby is true. Finally, suppose at the end of the day, instead, not only was she sweaty and dirty, but she was also injured, and in fact, she was also trying to hide a rugby ball from you. Now, what's the likelihood that you would observe her being sweaty, muddy, injured, and hiding a rugby ball if she hadn't actually played rugby? Well, presumably that's quite small, and maybe it's only a 2% chance, right? Very unlikely that you would observe these things if the assumption that she didn't play rugby is true. And so now let's evaluate our initial assumption, whether or not she played rugby, based on the likelihood of observing what we actually did. And again, we will reject this assumption if there's only a very small chance that we would have observed that if she hadn't actually played rugby. Well, there's one case here which fits that, right? It's the 2% case. That seems sufficiently unlikely to be observed if she hadn't actually played rugby. And so when the daughter is sweaty and dirty and injured and hiding a rugby ball, right, that seems highly unlikely to have occurred or to be observed if she hadn't actually played rugby. Therefore, we will reject the assumption that she didn't play rugby. In the other cases, clean or just muddy, right, that's sufficiently likely if the assumption is true that she hadn't actually played rugby. There's not enough evidence to reject our assumption that she didn't play rugby. So it's really the same thought process when we're making statistical inferences via a hypothesis test. In that case, we start with an assumption that population parameter equals a specific value. For example, we might hypothesize that a regression coefficient in the population captured by beta equals 0, being tested against the alternative that it's greater than 0. To evaluate the plausibility of this initial assumption, we can think about, well, what's the chance of observing what we actually do with respect to a sample statistic if this null hypothesis is true. And so in particular, we can think about calculating the probability that we would observe a test statistic at least as large as the one that we drew from our sample if the assumption about the population parameter is true. And for this, we use the fact that sample statistics have a probability distribution, and we can find exactly the probability of getting a statistic at least as large as the one that we did. And so suppose in this case, we're hypothesizing that beta equals 0, then we have a sampling distribution for our sample regression coefficient, which if the sample is large enough and other ideal conditions are met, has a t-distribution, and it's centered at beta equals 0 because we are assuming that beta equals 0 with the null hypothesis. And now we want to calculate the chance that we get a test statistic as large as the one we did. So we take a sample, suppose we find a sample regression coefficient b. Now with the sampling distribution of b, we can find exactly the probability that we would get a test statistic as large as the one we did. And suppose in this case, it is 20%. Well, that's exactly a p-value, right? That's the chance of observing a statistic as large as the one we did if the assumption about the parameter is true. This parallels the rugby case in that you're observing your daughter and you see her being sweaty and muddy and hiding a rugby ball. What's the probability you would observe that if the assumption that she didn't play rugby was true? We assess that to be very small. Here, we're doing the same thing in terms of statistics. We assume the null hypothesis is true. What's the probability that we would get a sample statistic at least as large as the one we did if the null hypothesis is true? This is exactly a p-value, so in this case, with a one-tailed test, the p-value would be 20%. Now, what if we have a two-tailed test? The logic is the same, the calculation is a little bit different, because in this case, suppose again we get a sample regression coefficient of b, and we can find the probability that we would get a test statistic at least as large as the one we did. But in a two-tailed test, when we think about the probability of being at least as large, we have to also account for the fact that negative values of b would be equally strong evidence against the likelihood or the plausibility of the null hypothesis. So with a two-tailed test, remember, large means in absolute value terms, and it's not just the probability of being greater than the positive value, but also less than the negative value. So if it's 20% probability of getting a test statistic larger than b, to find the p-value in the two-tailed test, we also have to account for the fact that there's also a 20% probability of being more negative than the negative b. And so the p-value here in this case is 40% rather than 20%. But the logic here is exactly the same. What's the probability of observing the sample we did under the assumption that the null hypothesis is true? In this case, it's 40%. Again, this is similar to the logic in the rugby case. We're not assessing the probability that our daughter played rugby or not. We're assessing what's the likelihood of observing what we did if our assumption was true. So with respect to inference, suppose somebody is trying to make an inference about a population parameter based on seeing a sample. They start with an assumption about the value of that population parameter, and then can think about the p-value. Again, what's the likelihood of getting a statistic at least as large as the one we did under the assumption that the null hypothesis is true. If that seems unlikely, that is going to be evidence against our initial assumption. If that seems fairly likely, that is not going to be enough evidence to render our initial assumption false. So just like we considered 4 different scenarios with the father and the daughter, suppose we had 4 different samples. In the first sample, we have a sample statistic close to the population parameter. That might seem very likely to occur if the population parameter is true. Maybe in a second sample, the sample statistic's a little further away, but it's still reasonably likely, maybe 80%. In a third sample, that sample statistic is even further away from our hypothesized value. Well, that's going to be less likely to occur if the population parameter is actually equal to its assumed value. Maybe in that case, it's 35%. And consider a fourth sample where our sample statistic is even further away from the hypothesized value for the population parameter. In this case, we might calculate that that would only happen with 2% likelihood, 2% of the time, if our null hypothesis is true. And so now we want to consider, when do we reject our initial assumption? By thinking about how unlikely it is to observe what we did. And so if it's sufficiently unlikely, like in the case when there is only 2% probability of getting the sample we observed, then we will reject our null hypothesis. But in these other 3 cases, the sample we observed was not sufficiently unlikely to cause us to doubt the accuracy of the null hypothesis to a degree great enough to reject it. So this logic is the same logic that the father applied in trying to assess whether or not the daughter played rugby. Again, we're not able to assess the probability that the daughter played rugby. In statistical inference, we're not able to assess the probability that the null hypothesis is true or false. But what we can think about is, what's the probability that we would observe what we actually did if our initial assumption was true? And if it's very unlikely that we would observe what we did if the null hypothesis is true, that gives us enough evidence to conclude that the null hypothesis is false. Now, we won't ever know whether our assumption is actually true or false. We're trying to make a statistical inference or a decision where we can't see the full information, we can't see the population, we can't observe whether our child played rugby or not. We're having to assess this based on the likelihood of observing what we did if the null hypothesis or our initial assumption was true. But remember, this is not the probability that the null hypothesis is true or false. This is the probability of observing what we did if the null hypothesis is true.